our next talk, we have David Kale, who's a research engineer at the Children's Hospital in LA, and he works at the Virtual Pediatric Intensive Care Unit. So he will tell us all about using machine learning in a clinical context.
Sure. My name's Dave Kale. I work as a data scientist in the Virtual Pediatric Intensive Care Unit at Children's Hospital of Los Angeles. The VPICU, as we call it, is kind of a unique research group. It consists now largely of computer scientists as opposed to clinical researchers. And we spend a lot of our time doing sort of data-intensive research. The VPICU, just briefly, was founded about a little over 10 years ago by my boss, Randall Wetzel. He's Director of Anesthesia and Critical Care Medicine at CHLA. And basically, his vision has been to improve the quality of care delivered to critically ill children using IT in general. They've done projects ranging from telemedicine to distance learning to building algorithms for predictive modeling and risk stratification to do benchmarking and various kinds of things. In the last few years, there's been increasing focus in our group on applying data mining and statistical learning to the increasingly large amounts of data that are being gathered in commercial electronic healthcare record systems. So intensive or critical care, for those of you who don't know, is essentially the level of care delivered in hospitals for patients who are not in need of immediate emergency care to save their lives, but still are in a condition that could potentially be life-threatening. And they require really, really close monitoring and usually very specialized kinds of care. What you find in intensive care units is the highest staffing ratio, so a lot more clinicians per patient than you find in other parts of the hospital. And you also find the highest level of surveillance. So when you think of popular media depictions of medicine and you think of patients that are hooked up to all kinds of machines and monitors and stuff, that's usually what they're depicting as intensive care. And that's what you see going on in here. This is actually an image from a neonatal intensive care unit, but you just see there's an extremely high amount of surveillance. There's lots of machines either monitoring the patient or maybe intervening in the patient. You also have clinical staff recording a lot of observations. So it's a very data-rich and data-intensive environment. From a machine learning standpoint, it's very interesting because there's a lot of data to work with. From a clinical person's perspective, this is the cognitive load or cognitive burden on them is getting higher all the time. The amount of data that's being gathered and then represented to them is really increasing, and they're having a hard time managing it. So there's a real need here to build tools that help them sort through the data. So I'm actually going to spend, this is my outline, I'm actually going to spend a large part of my talk talking about the data that we're working with and the kinds of problems we're interested in working with it, because I actually think that's what will be most interesting to this crowd. I will get a little bit into some of the models that we've built and some experimental results, but mostly I want to focus on the nature of the data, because our intuition is that it's very similar to some of the domains that I've seen presented throughout the week, but also subtly different. And we're very curious to sort of check our intuition against what you guys think. So I'm really excited to hear your feedback during the Q&A and then also later tonight at dinner, hopefully. So here's the kind of data that in an ideal world would be available from the PICU, from the Pediatric Intensive Care Unit. So you have a lot of vital signs and heart rates and things like you'd expect, lab tests, clinical assessments, medications, treatments, notes, diagnoses, yada, yada, yada. In the real world, where we're dealing with hospitals, actually at maybe like 60–70% of hospitals, you're not capturing any of this digitally because they haven't adopted electronic healthcare record systems yet. If you're lucky and you're at a hospital like mine where they've made the massive investment to get one of these systems, you're still only capturing certain kinds of data. In particular, at most hospitals who have a sort of typical commercial EHR deployment, they're not capturing the really high frequency stuff. So we don't have necessarily the same problem that a lot of people describe, where you're just being bombarded by way too much data, more than you can even archive or record, because most hospitals just haven't made the investment for that. Usually you find that at really advanced research institutions. And so, for example, my hospital, we have a jury-rigged system to get some of the high-frequency monitor data. We don't capture any waveforms whatsoever. So really, our focus is on the data that you get in commercial EHRs. If you've paid out the money for it, what do you get? And in particular, what you'll find with all the data that I've listed here that's marked in red is every piece of data that goes into the EHR has been manually verified by a clinician or a human being. So we're not automatically capturing this data. Human beings are actually either entering it or at least checking it. And the data that we're particularly interested in is what I'll call PICU observational time series. So we do have vital signs, but it's not sort of high-frequency waveforms, but rather it's samples of it that human beings are recording, and then things like lab results, clinical assessments. Clinical assessments are sort of subjective assessments where a clinician will look at the patient and then record some kind of observation. Oftentimes things related to, for example, cognitive function. So what this data looks like, it's very high dimensional. There's potentially hundreds of variables that could be recorded at any one time, but usually we're only recording subsets of them, so it's sparse. It is by nature episodic. In other words, we start recording data when a patient comes into the unit, and when they leave the unit, we stop recording data on them. And I think one thing that sets it apart from some other scientific domains maybe is we're looking at observations from a large number of individuals, not as opposed to sort of pointing at a single system or at a single scientific phenomenon. The patients are obviously all human beings, so they're similar in that sense, but they also have unique differences, and the disease processes they're going through are different as well. And then, as I've emphasized several times, all of this data is manually entered or verified by clinical staff, which has some interesting implications about how much data we get and also even the very nature of the data we're recording. One of the issues that we have noticed with the data is that is an alignment issue. So we start recording observations when the patient comes to the unit, not starting at the onset of illness. So you can imagine scenarios where two patients have exactly the same disease, maybe even the same time course, but if one of them came in with less time transpiring between the onset of the disease than the other one did, then we won't even have necessarily the same data about them, at least starting at sort of time zero when they entered. So alignment's an issue. The episodes also vary widely in length. The duration of a PICU episode could be anywhere from a few hours or days to even weeks or months, particularly for patients whose reason for being there is related to maybe some complication with a chronic disease. This is a histogram that I made of length of stay in days from a data set of about 10,600 episodes. You'll see the vast majority of patients are in there for less than a week, and even a lot of them are there for 1 or 2 days, but there is a long tail going out to even months. And so obviously sort of doing, if you're trying to do sort of like one-to-one comparisons of 2 episodes to see how similar they are, this makes it somewhat non-trivial. I think the sort of the most significant aspect of this data is the fact that it's the irregular sampling rate of it. Basically, we only have measurements when a human being records them, and we're not doing it systematically. There's no rule that says a person must record a heart rate every 5 minutes or even every hour. There are general hospital policies like that, but human beings can choose not to follow them. They can record things more frequently if they want to. They can record things less frequently if they want to. The measurement times are also not aligned. So there's no, to the extent that there are policies about when to record data, there are things like record it on the hour every hour. So if patients were admitted sort of at different times, then they will be getting the recordings recorded at different amounts of time after their admission. So like, for example, you record heart rate at 7 p.m. If one guy was admitted at 6 p.m. and one guy was admitted at 6:30 p.m., then the sort of relative time to their admission when that measurement is recorded is different. So the measurement times are not aligned at all. And then the sampling varies sort of within and across episodes as well as across variables. To give you a flavor, here's 13 variables from the data set I mentioned. And as you can see, we've calculated the sort of average measurements per day for each variable. So it ranges from things like heart rate and respiratory rate, where you're recording it maybe once an hour, a little more frequently than that, all the way down to glucose and pH, where you get lucky if you're getting it once or twice a day. Bias and interpretation. This is sort of an even more subtle thing that we noticed as we worked with this data. For one thing, we believe that there's sort of a certain amount of sample selection bias in the values that are recorded. Clinicians or clinical staff are more likely to record abnormal values. If the patient is healthy, particularly let's say at the end of their stay, they're doing fine, they're going to be discharged in a few hours, the clinical staff may just stop recording measurements altogether. But if the patient's condition is steadily getting worse, the clinical staff will start recording heart rates, for example, more frequently, maybe as often as every 5 minutes. So there's actually information in how frequently the measurements were recorded. More subtle, something that we've come to realize is that what's actually being recorded oftentimes is not a raw measurement, not an actual observation of a heart rate, but rather a human being's interpretation of the patient's state, or a summary statistic. So I had a conversation at lunch today with some gentlemen talking about doing summary of streaming data so you don't have to record all the data because there's too much, and trying to come up with algorithms for creating summaries of the streaming data so you can write that down and being able to go back from that to the raw data. And you could think of this as sort of similar, that human beings are actually creating summaries of data as opposed to recording raw measurements. That's something that we've recently realized is very subtle. There's also evidence of non-random missing data, where basically the very presence or absence of measurements gives us information about the patient's illness. So a good example is end-tidal CO2, a measurement of the amount of carbon dioxide that a patient is exhaling. You're only going to have measurements of that if the patient has an assistive breathing device that's recording it. Patients get assistive breathing devices when they need them, or rather when a clinician thinks they need them, which tells you something about their level of illness. So whether we have end-tidal CO2 measurements or not actually gives us information about the patient's illness, and even maybe information about what values we should expect to observe in other variables. So it's clear that you can't really, it's definitely not missing at random. And you can see here in this histogram, in the data set that we're working with, this is actually fairly common, that there's a significant number of episodes that have no measurements of end-tidal CO2, no measurements of pH, that sort of stuff. I'm not even going to mention the effective interventions, but obviously we're not passively observing these patients, we're actually actively doing things to them all the time, and that's changing the underlying physiology. That's another big challenge. So I want to talk briefly about a model that we've applied. The analytic task that was given to us by our clinical colleagues was, we want you guys to try to cluster PICU episodes. We would like you to try to put these patient episodes in groups where they're similar physiologically, and then we want to see if those clusters correspond to sort of known clinical phenomena. A somewhat sort of kind of unusual task. It's different from a lot of traditional, I think, medical tasks or even time series tasks. Our priority early on, especially since this is a new problem for us and a new field for us, and in particular, I think it's actually relatively just a new kind of research in general because this data just really didn't exist 10 years ago. So our priority early on was we're going to do something simple, use a simple model, something that we understand well, that we can implement and that will run computationally efficiently in the presence of the missing data. The missing data thing creates a big problem. So we went with just basically a mixture of diagonal covariance Gaussians, so something straightforward that basically everyone in this room could implement. That imposed constraints on us. Our data need to have finite dimensions, so we truncated episodes at 24 hours. Obviously, that's the kind of thing that makes a machine learning person scream. If you have a patient that was there for a week, you're throwing out 6 days worth of data. It's not entirely unjustified. Our clinical colleagues assure us that all the real action is happening in the first 24 hours, so there's some sort of justification for it. We also discretize time into 1-hour blocks and then bin measurements within those blocks. And that, of course, creates a new missing data problem for blocks where there aren't any measurements. So we go ahead and make a missing at random assumption with our model just to be able to handle that. We have to go Bayesian, use an empirical Bayesian prior, because you could imagine there might be really small clusters where you actually have no data for certain parameters because of this missing data problem, which would cause learning to blow up. And then we also did something where we used basically a kernel-based smoothing prior on our mean parameters. The purpose of that is we're not modeling the data as a trajectory with this model. We're sort of modeling each variable at each time slice as independent. But this smoothing prior gets the model to try and learn parameters that look kind of like trajectories. It's sort of a poor man's Gaussian processes. And that's sort of the direction we're heading in for a next step. We have a paper, and the details of this are described here. The generative process that this sort of describes would basically be sample your patient from one of the clusters, and then for each variable and each time point, sample from a Gaussian distributed around the mean, and that's how you get the measurements. Obviously, this is not an accurate description of how these things happen. This in no way resembles patient physiology, but the question is, can we do something useful with it? And that's what this is my boss, Randall Wetzel, that's their main concern. And in particular, they want to know, do the clusters seem to correspond to known medical phenomena? And also, maybe do they have some kind of prognostic significance? So let's talk some experiments and some results. For our experimental setup, we just followed sort of a standard 5-fold cross-validation procedure. We took our data set, we split it into 5 splits, and then we ran our experiments using different splits as training and validation and then test, and sort of ran a whole bunch of different iterations. We also ran experiments with different numbers of clusters to experiment to see how that might affect the results that we get out. So what you see here in the top row is mixture proportion, which is roughly sort of what fraction of the patients were assigned to each cluster. And what you see in the bottom row is the probability of mortality in each cluster. So roughly how many patients assigned to each cluster died. And this thick black line here is the overall mortality rate in our data set, about 6%, which is sort of standard for pediatric critical care. And so the results seem interesting. In each case, there seem to be clusters that have much higher rates of mortality than other clusters, and some very low. And in particular, it looks like that mortality is not randomly distributed across clusters. You could do like a t-test to check that, but we weren't too worried about it. So we could do the same thing with diagnoses. We looked at the distribution of neurologic-related diagnoses across one run of a 20-cluster model. And you see kind of the same pattern here, that there seems to be a couple clusters that seem to have way more neurologic patients than some of the other clusters. By no means definitive. We haven't discovered an algorithm that can find all the neurologic patients based just on physiology. But it seems interesting enough at least to excite the doctors. Another thing we came up with to sort of help us assess what this is doing was to just visualize the mean parameters. So what we did is, for example, we took for one cluster, we took the diastolic blood pressure mean parameters for hours 1 through 24 and the variance, and graphed it as this blue line with the shading. And then for the whole data set, that's what the red is. The red line is the mean and the red is the variance. And so what you see with this cluster, which is a high mortality cluster, is in general, low blood pressure, prolonged cap refill, high heart rate, high respiratory rate, that kind of stuff. And the doctors looked at that and said, that looks kind of like shock. That's interesting. So our thinking is that maybe this can be sort of a useful kind of data-driven sort of decision support to deliver. If you can go into a database and find patients similar to a new patient and do visualizations like this, that will help the doctor not necessarily diagnose or predict, but generate hypotheses about what might be going on with their patients. So sort of a passive decision support, kind of almost like a sort of information retrieval type task. The idea being here that doctors hate black boxes that tell them what to do. This one thing is very, very clear. They don't want computers to make predictions for them. So anyway, we also did, in terms of evaluating our results, I'm not going to get into it too much, it's in the paper, but we also did something where we basically did mortality prediction built on top of our clusters. And we showed that training a logistic regression that is a mixture of logistic regressions trained for each cluster does better than just doing good feature selection and training one logistic regression. So it's interesting, it's promising, it's very early work. In terms of sort of next steps, what we're very interested in, we have a number of different collaborations, people who have this data set who are trying different things. Our colleague Ben Marlin, with whom this work was done, is at Massachusetts Amherst. He's got a student working on Gaussian processes. We also have given this data set to a gentleman named Kristen Shelton at UC Riverside, who does continuous time Bayes nets. And this fall, will be starting my PhD at USC, and I'll be working with Yang Liu, who presented earlier this week. And she has a lot of interesting ideas about things to do with this, so we're going to work on some of these problems too. The broader picture, it's a really rich data set, and in general, I think that intensive care units are producing really, really rich data. And if we could get capture of the high-frequency monitor data, it'll be even richer. It's obviously a very impactful problem area. The amount of healthcare dollars that are going into intensive care is enormous. It's kind of surprising that there isn't more sort of interest in funding from the NIH to try and solve this problem, because ICUs are definitely probably among the least efficient kind of medical care delivered. So it really needs to be solved. There's a lot of different interesting potential research directions. There's the potential to go sort of the kind of work we're doing, where we're just pretending we don't know anything about medicine and just throwing machine learning at it. You can also go into really getting into computational physiology. There's a lot of cool work going on at places like here at UC Berkeley and also at MIT. Our goal is decision support via similar patients. So we're really thinking of this as sort of an information retrieval problem. In terms of data sets, if people look at this and say, this looks like fun, I'd like to work on something like this, we're hoping to publish some of our data sets very soon. We're still working out the legal stuff, but it's definitely doable. It's going to happen, and we'll probably do it as a competition first through Kaggle. And there's also the Mimic 2 project through MIT. You can get a massive data set, including high-frequency monitor data, that's just like ours if you want to do this kind of work. In fact, I believe there's actually a competition going on with the Mimic data right now. Also, we run an annual symposium, the Meaningful Use of Complex Medical Data Symposium. First one was last year. This year's is going to be August 9 through 12, and it's every year. I think it's going to be at Children's Hospital LA. This is the website, mucmd.org. And last year's talks are at YouTube. We had some awesome people last year. We had Stuart Russell, we had John Langford, and a variety of other really, really smart people who you can see their talks online. So we hope you have interest in joining us, and keep your eyes out for potential competitions. So.
We have a few minutes. We have a few minutes for questions from the audience.
Have you tried supervised learning at all? It seems like you're trying to be agnostic to what people would actually say about these different clusters, but if you sort of embed yourself with a bunch of doctors who know about each patient intimately, is there something else to be done here where you're not using k-means, but you're using something else in supervised?
Yeah, I think so. I mean, I definitely think that there's a lot of potential there. I'll be honest with you, a lot of our work is driven by a certain ideology from my boss, Randall, who what one person would call clinical knowledge, he would call clinical bias. And so he was really sort of enamored of unsupervised learning. He likes this idea, so that's what a lot of our early work has been. I've been thinking about things where you could maybe do sort of weekly supervised learning, like maybe if you know that two patients both receive the same diagnosis, rather than trying to like build a regression model of diagnosis, what you could do is do some sort of like link prediction problem where you draw a link between patients who share a diagnosis, and maybe try to push your metric learning algorithm, which is essentially what we're doing, toward learning that patients with links are closer than other patients. So I think there's a lot of potential there. We just haven't gotten there yet. It's something we're interested in doing, I think.
Any other questions from the audience? Yes.
Regarding the missing data, has this identified any missing data that, in the sense of we should be monitoring this for every patient? Like when I go into my hospital, they always check my blood pressure every single time, whether I'm there for a cold or anything.
That's an interesting question. I don't think we've thought much about that, but certainly I think that would be worth doing. With things like end-tidal CO2, for example, you only have that when you're doing an intervention, but you could imagine things like pH and glucose you derive from an invasive blood test. And doctors tend to only order it when they expect to find something. So you could imagine if you're doing, I think our work probably wouldn't be particularly good for that. You would probably want to do some more traditional like state estimation type stuff, but you could imagine sort of maybe having some kind of distribution over an estimate of pH. And then making suggestions like, hey, you should order a test. Either this looks like it's going to be bad, or we're really uncertain about what it might be. We need information. So you can imagine do that. I do have a colleague who's working on things like that with our collaborators from UC Riverside with regard to estimating pH from other non-invasive variables. But it's really tough. They're actually having a very hard time with
it. This data is also very useful for doing retrospective analysis or observational studies.
Mm-hmm.
And I think clinicians approach it often by needing to identify confounding variables or do propensity analysis to be able to equalize the illness in patients before they actually evaluate them. I was just wondering, I think there's implications for machine learning in those sort of analyses being done because they're rooted in statistical community from a while back.
Yes. Yeah, that's actually a lot of, my boss has done a lot of work that I would say fits in that category. The main sort of measure of performance in intensive care is mortality. How many of your patients died? The main problem with that is the fact that it really depends as much on the basic sort of illness of the patients that are coming in as it does on the level of care being delivered. And like at a hospital like Children's Hospital of LA, all the area hospitals are helicoptering in their most difficult patients because they can't deal with them. And so for like the last 20 years, one of the main areas of research in this area has been doing risk stratification in pediatric patients populations in order to do sort of like standardized mortality ratios and stuff. So I think there's a lot of interesting stuff there. Actually, if you go check out the talks that we had at our MuckMed thing last year, there was a couple cool talks from John Langford and his wife Alina Begelzimmer about sort of possible sort of results from theoretical computer science that could be useful for doing sort of better clinical trial design or adaptive clinical trial design that I think would be useful for that. And then there's, I don't know if we record it, but there's also an excellent debate between Dr. Langford and Professor Russell about John's stuff versus doing Bayesian clinical design. So that's why in my opinion, that's why this MuckMed meeting was such a great meeting. We got some really smart people to come and think hard about medical problems. So I definitely, if you guys are interested in this, I encourage you to come.
Thank our speaker again.
In the real world, where we're dealing with hospitals, actually at maybe like 60–70% of hospitals, you're not capturing any of this digitally because they haven't adopted electronic healthcare record systems yet. If you're lucky and you're at a hospital like mine where they've made the massive investment to get one of these systems, you're still only capturing certain kinds of data. In particular, at most hospitals who have a sort of typical commercial EHR deployment, they're not capturing the really high frequency stuff. So we don't have necessarily the same problem that a lot of people describe where you're just being bombarded by way too much data, more than you can even archive or record, because most hospitals just haven't made the investment for that. Usually you find that at really advanced research institutions. And so, for example, my hospital, we have a jury-rig system to get some of the high-frequency monitor data. We don't capture any waveforms whatsoever. So really, our focus is on the data that you get. So I'm actually going to spend, this is my outline, I'm actually going to spend a large part of my talk talking about the data that we're working with and the kinds of problems we're interested in working with it, because I actually think that's what will be most interesting to this crowd. I will get a little bit into some of the models that we've built and some experimental results, but mostly I want to focus on the nature of the data, because our intuition is that it's very similar to some of the domains that I've seen presented throughout the week, but also subtly different. And we're very curious to sort of check our intuition against what you guys think. So I'm really excited to hear your feedback during the Q&A, and then also later tonight at dinner, hopefully. So here's the kind of data that in an ideal world would be available from the PICU, from the Pediatric Intensive Care Unit. So you have a lot of vital signs and heart rates and things like you'd expect, lab tests, clinical assessments, medications, treatments, notes, diagnoses, yada, yada, yada. Listen to distance learning, to building algorithms for predictive modeling and risk stratification, to do benchmarking, various kinds of things. In the last few years, there's been increasing focus in our group on applying data mining and statistical learning to the increasingly large amounts of data that are being gathered in commercial electronic healthcare record systems. So intensive or critical care, for those of you who don't know, is essentially the level of care delivered in hospitals for patients who are not in need of immediate emergency care to save their lives, but still are in a condition that could potentially be life-threatening. And they require really, really close monitoring and usually very specialized kinds of care. What you find in intensive care units is the highest staffing ratio, so a lot more clinicians per patient than you find in other parts of the hospital. And you also...
Our next talk, we have Kale, who's a research engineer at the Children's Hospital in LA, and he works at the virtual pediatric intensive care unit. So he will tell us all about using machine learning in a clinical context, actually.
Sure. My name's Dave Kale. I work as a data scientist in the virtual pediatric intensive care unit at Children's Hospital of Los Angeles. The VPICU, as we call it, is kind of a unique research group. It consists now largely of computer scientists as opposed to clinical researchers. And we spend a lot of our time doing sort of data-intensive research. The VPICU, just briefly, was founded about a little over 10 years ago by my boss, Randall Wetzel. He's Director of Anesthesia and Critical Care Medicine at CHLA. And basically his vision has been to improve the quality of care delivered to critically ill children using IT in general. They've done projects ranging from telemedicine to find the highest level of surveillance. So when you think of popular media depictions of medicine and you think of patients that are hooked up to all kinds of machines and monitors and stuff, that's usually what they're depicting as intensive care. And that's what you see going on in here. This is actually an image from a neonatal intensive care unit, but you just see there's an extremely high amount of surveillance. There's lots of machines either monitoring the patient or maybe intervening in the patient. You also have clinical staff recording a lot of observations. So it's a very data-rich and data-intensive environment. From a machine learning standpoint, it's very interesting because there's a lot of data to work with. From a clinical person's perspective, this is the cognitive load or cognitive burden on them is getting higher all the time. The amount of data that's being gathered and then represented to them is really increasing, and they're having a hard time managing it. So there's a real need here to build tools that help them sort through the data.